All right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you with us today, help us to use this time wisely to review for the test, and that you just settle any remaining questions. Lord, in your name I pray, Lord Jesus. Amen. All right. Let's see here. So, I was looking back, and I think that the quizzes are pretty representative in some sense. But there's one thing I think that's missing from the quizzes. Don't worry, I'm not going to give one today to make up for it, because to do that would require some significant amount of time, because I'm talking about the complete series solution. So that is definitely on the test. I usually test on it, but it's not something I can kind of just shove into a 10-minute quiz, right? Because the complete series solution does take some time, So, all right. Anyway, so let's see here. So this is the quiz I just collected. Any questions about it? You just want me to just go through the solution? I guess we could do that. Find my laser. All right. So this first one, so with any inverse Laplace transform problem, first order of business is to understand the denominator. So I factor it, then I do partial fractions, and lo and behold, I get this. Once I have that, then I can take the inverse transform. I get a minus 2, I get a 3t, I get a 2e to the minus t. Yeah. And then similar story for the next part. Again, partial fractions. And then I can do the inverse transform once I see that, like so. All right. Of course, the other way you could do here would be to complete the square and do it in terms of cosh and sinh. I don't recommend that. It's got fractions. It's not pretty. Anyway, problem 2, which is probably the thing, if I had to guess, is probably people's most likely weakness on this test. Just power series methods, right? And there's nothing especially exciting here. You just have to put in the power series and be careful and work out term by term what happens. So, since we're centering at 0, it looks like this, right? If I was to center somewhere else, I'd have to do, x minus x naught squared, and so forth. Why is there no constant term here? Y of 0, 0, right? So don't forget the meaning of the initial value and the initial derivative. That gives me the coefficients respectively of the 0th term and the first term. This is Taylor's theorem. Or if you like, it's calculus 1. Those are the the coefficients that you see on the equation of the tangent line, right? The y-intercept and the slope. Okay, so so I differentiate 2 times. Try to keep as many as I think I might be interested in. Threw in the 12a4x squared just for kicks. Technically, I said find the first 3, so I didn't actually need that. If you look at it, really, I could have stopped at just the constant and the x's here. That would have sufficed. So as I look at this, I've got this 2a2, right? And nothing else over here has a constant in it, right? Because this thing starts at x squared. So there's no constant term in here to be found. So it's just this up against whatever's over here, which happens to be a 1. By the way, make sure you know your geometric series. Exponential, sine, cosine, this, if you didn't understand, is I'm using the geometric series with, the ratio of, man, I can't even see from here, good grief, x squared. So that's 1 plus x squared over here, coming from the geometric series. So then, of course, I had to multiply these out. And when I do that, I get these are the first 3 terms. So that's what I have on the right-hand side. So I've got 2a2 equal to 1, which, of course, gives me a2 is a half. I already know that a1 is 1. That was given in the initial condition, So there you go. I got 2 terms at this point. I need 1 more. So if I look at the x, I got 6a3 over here. There is no x term in here, right? Because the lowest order possible here is x cubed. You see that? This times that gives me x cubed. That's the lowest possible order in this product. So that just gives me 6a3 equals to 2. And that gives me a3 as a third, right? And then, because I'm curious, I decided to get one more term. So past this, of course, I've got the 12a4 equals to the coefficient of x squared over here, which is 3. Notice there is no x squared term from here because, again, this starts at order 3.
Will we get bonus points on the test if we solve for extra terms?
No. No. There's time to do the problems I've assigned. There's not problems to do more of problems that I didn't ask for. I mean, I might be impressed, possibly, but don't do that at the expense of other problems. Because if I ask to find the first 3 terms problem, it's not meant to take a lot of time. You know. Anyway, any questions about this? Yeah.
So when we're writing out the series, would you recommend just writing out the first 3 terms, just the first few terms? Because yesterday we were going through it, we went to like x to the 6, which we deemed was like completely unnecessary.
Right. Yeah. Fair enough. I mean, you kind of need to. Writing down more doesn't make you understand more, right?
Yeah.
So you have to kind of see where you're going. Once you identify that this term starts with like x squared, I mean x cubed, it kind of indicates that maybe we only really care up to quadratic order terms for the differential equation. However, caring about quadratic order terms for the differential equation still makes you care about the 4th order term on the y prime prime. You know, because the differentiation twice pulls the power down by 2, so it does end up. The second derivative term always ends up like interlinking higher powers with lower powers is what always does in terms of the algebra. But yeah, what exactly you should write down? I would say, you know, write down as a typical rule of thumb. I write down like 3 terms, and then I work on it, and then I just keep in mind that in that plus dot 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 there are other things, and so be careful. You know, that you haven't written down something that you should be counting. You know, that's just the thing to watch out for. So the plus dot 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 is, you know, just something not to write. It's not something to not think about. This one actually is kind of fun. It wasn't too bad. So I did the substitution like you guys like, and I substituted, and then I solved for the big Y, and I got this, and then I inverse transformed, and I got that, and then I plugged this in here, and then I had a moment of despair, like, what's going to happen? And then I realized, just make a common denominator, and then the stuff I don't know what to do about cancels out, and I'm just left with things that I can inverse transform. Yay. So I also have a leg up on this problem, like, because I already know, generically speaking, what the solution should look like from our work on eigenvectors and the 2x2 eigenvector problem, right? A problem like this, it only has, you know, solutions that are either exponentials, sines, or cosines with exponentials, or exponentials times time, right? I can't have, like one of you guys showed me a solution, like when you're still working through things, and you had like a sine in the one and like a cosh in the other, and I immediately knew that was wrong, because there is no solution like that for the 2x2 system, right? They always either come in a pair of like eigenvector solutions, or the generalized eigenvector paired with the eigenvector solution, or the complex eigenvector solution, and those have a particular, you know, collection of functions. So, but there are new things that could happen here, right? Like an uglier version of this problem would be if I put unit step functions as the inhomogeneous terms for this one. You know, then we would definitely be seeing things we hadn't seen before in the, you know, eigenvector problem. So in fact, this was a homogeneous problem actually, right? Like there was no forcing functions in this problem. You know, if I added like plus t here and plus e to the t here, that would be a different animal, you know. So It's too late to apologize. It's too late. I'm just kidding. That was just a lame excuse to say something. I have your other thing. I can find it. There it is. Thank you. So, it was pointed out to me that I took points off somebody's for the right solution to, let's see here, if I can find it. So I made a mistake in this solution, which I don't think I've fixed yet. That is supposed to be a 6. So if it looks like I took point off your quiz and you'd like your point back, let me know. I think it actually only happened to one person. I think for the most part, people are like not quite done with this. Like you're kind of mid-thought process on that. You're not quite finished with it, so I just took off 3 or 4 depending on the severity of the incompletion of the thought. But let's see here. So let's take a walk down memory lane and look at some old quizzes, you know. So this one here was kind of fun. We had singularities at 3 plus or minus 2i. We had another one at 10. And then I, gave you, we were looking for a series solution centered at 9, what's the disk of convergence there? It is radius 1, as it turns out, which intersects with the real line. 8 to 10 would be my open interval of convergence. Over here, the closest singularity to 1 are these complex singularities. And so they're my open interval of convergence goes from 1 plus or minus 1 minus the square root of 8 to 1 plus the square root of 8. The square root of 8 is the distance from the center to the singular point, because we're going 2 over and 2 up. The square root of 4 plus 4 is the square root of 8. Any questions about this? So I do try to ask at least one question on the test about the open interval of convergence for solutions. So I usually test on this. It's not a big part of the test, but it's there. So this was just to try to get you guys, going on the power series. This is less likely to be on the test because this is just part of, like, problem 2 just appears as parts of another problem, No need to test it separately. Where'd my 10 go? Oh, there it is. Let's see here. Oh, wait a minute. Oh, that's right. I was like, wait a minute, didn't I just... Oh, deja vu. That's right, I did that, didn't I? But I fixed it. I fixed it. So that one's different. But okay, so here again... So Jordan, you were asking me, do I need to write all the first 6 terms? That's not really what you asked me. I'm just, reinterpreting your question in a more rude way, as is my right, on the basis of my adversarial pedagogy. But, oh, look. I was like, we need to be, oh, there's the plus ... That's kind of, I guess I forgot to put the ... Sorry about that. But anyway, again, the thought process is the same. We look for, how can I have constant terms? How can I have linear terms? How can I have quadratic terms? The only place constant terms are coming from is on the second derivative. The only place linear terms are coming from is on the second derivative. So that makes A2 and A3 both 0. On the other hand, when I get to order 2, I got that 12A4 term, and all of a sudden it's coupled to the A sub naught term, And then I can solve for A4 as minus 1/12 A naught, and so forth. And that's all I need, because I was also given y of 0 is 1 and y prime of 0 is 2, which gives me this 1 plus 2x here, like so. So what if instead of just the first 3 terms here, we were looking for like the complete series solution? How would that look? What would the difference be? Because I take a pretty different approach when I'm looking for the complete series solution, right? I don't write down this. I write down the summation, n equals 0 to infinity. I plug it in, and I try to work out like what's the formula for the recurrence relation on the nth term. You know, we'll look at those solutions. We'll look at that in the team mission solution in a second here, okay? But I just would point out that the approach for the complete series solution and the calculation approach for like the first three terms, they're somewhat divorced, you know? At least in my mind. Of course, you could always approach everything like the complete series problem and then just look at the formulas from your complete series solution for like lowest order, but I don't recommend that because it doesn't usually go well. It's just easier to do the plus dot dot thing to find the first three terms as opposed to you know, finding a general solution and then just specializing it. I think it doesn't usually go well. Well, it doesn't go well for me. Maybe I'm just a special case. I don't know, but I do test Cauchy-Euler, of course. I think you guys welcome the Cauchy-Euler, right? Cauchy-Euler are essentially a gift on this test, aren't they? Because it's pretty just, you just write down the, you know, the characteristic equation, which just comes from differentiating x to the power r. Solve for r, then you get c1 x to the r1 plus c2 x to the r2. Unless, of course, there's a complex root. If there's a complex root, you need to know this. This absolutely must be on your formula card if you don't already know it. You must know how to, you know, write down. Because if I ask for the general real solution, and you just give me x to a complex power, I'm going to take points off because that's not the answer. So just to be clear, if I have x to the alpha plus I beta, we can basically think of that as x to the alpha times x to the I beta, which we can think of as x to the alpha exponential of beta I times the natural log of x, which is x to the alpha cosine of beta log x plus I x to the alpha sine of beta natural log of x, right? So the real part of x to the alpha plus I beta is x to the alpha cosine of beta log x. The imaginary part of x to the alpha plus I beta is x to the alpha times the sine of beta times the natural log of x. Now I'm assuming something here. I'm assuming that x is positive, okay? But this and this, right? Those are the real functions that we use a linear combination of to form our general solution for such a problem, right? So that's what I did here. Here alpha was -2 and beta was 3, so I end up with this solution. And of course, like in this kind of problem, I don't require you to write this down, you know? Like you can jump straight from here to there. That's completely legitimate in here. The reason I'm writing this down is because I understand complex analysis enough for this problem, this step to make sense to me. So this is a meaningful, like, you know, middle step. If you haven't had complex analysis, or if you're not comfortable with complex analysis, I don't expect you to write this down, but perhaps you'll join us for complex analysis and then it'll become, you know, more natural to you. I don't know. But, and I was going to white that out. I'm sorry. Sorry about that. I don't know how that happened. Let's see here. And the double root case is kind of funny, right? So when we have the repeated root, if you have a repeated root in the Cauchy-Euler problem, you have to multiply by log x instead of, like the repeated root case for the constant coefficient, we multiplied by x, right? Like if we had lambda equals to 5 twice, we do what? E to the x, and then x times e to the 5x, right? For some reason, in the Cauchy-Euler problem, we end up multiplying by the natural log of x. If we had a three-peated root, like if you had lambda r equal to 5 three times, you'd end up doing natural log of x squared, like natural log of x quantity squared times x to the power 5. That would be your next solution. But that won't happen because what did I do? I limited our discussion of regular singular points to what? Order 2. So the three-peated root is unavailable to us. Mm. Welcome. Oh, that reminds me, I should, now that everybody's here, hand my attendance sheet around. You can add a date if you don't mind. Thank you, sir. All right. Jack's quiz. Yes. I remember this. This is a history-making quiz for me. I never given 2 quizzes in one class period before this. So I think most of you didn't understand that when I said that the next quiz would be open notes, I wasn't talking about notes from a future day. I was talking about the notes you're about to take. But anyway, silliness aside, this is the Laplace transform. You should know the definition of it. You know, I probably don't ask that as a test question because you got a note card, so it's just a dumb question as long as you got a note card, right? In a world where you don't have note cards, though, that becomes a test question. But that's not a world you want to live in, I'm guessing. So the Laplace transform of, oh, look at the simpler times, right? Laplace transform of this is that. Laplace transform of this is that. Yep. Laplace transform of that is that. All right, well, great. So we worked these out that day. Where am I? Then we're back to 13. So, you know, do spend some time making sure you understand how to deal with the exponential. That's a weak point for most of you. If you don't understand that, if you're not completely bored with how that works, you should open up the textbook, go to the section on, you know, discontinuous functions in the Laplace transform and work like 5 problems there. Yep.
So is it our note card plus the piece of paper for Laplace?
Oh, my bad. I meant, when I say note card, I meant the paper. The paper. You just get the paper. There's no note card. Thank
So
you.
You can write on the back of it?
You may write on the back of it. You may write between the lines if you want.
Okay.
You can, you know, write on top of it with invisible ink if you've got the proper UV light to bring it out during class, but don't shine it at other people's eyes. You know, be considerate. Let's see here.
Can we shrink the boxes on the front?
Yeah, if you want to take the existing formula sheet and run it through a copy machine, shrink it down. You're also allowed to do that, yeah. What I'm really saying is that you get a page of notes, but I would strongly advise bringing this page of notes because, you know, it has good stuff on it. Let's see here. Okay, so however, on the final exam, I will not allow the page of notes. On the final exam, you will just have this paper, but not this paper with writing. I will provide this paper for the final. Yeah.
Did you get an index card?
You can have 4 index cards for the final, though, yeah. All right, let's see here. Let's see here. Let's go back to, all right, like here's, I guess this one's as good as any to look at. Thank you, sir. So here we have, you know, a typical find the complete series solution. So what's the method? I, you know, take a complete series solution. I twice differentiate that thing, right? And then I plug it into the differential equation, which here is just y prime prime is xy. At x equal to 0, where's that appearing? That's appearing in the sense that I'm looking at a sum of powers of x, right? If I said solve the differential equation at like 1, I would need to look at like an x minus 1 to the n, you know? what I didn't. I said find the solution centered at 0. So we're doing that. So I plug it in. And then what's my next move is to notice that I've got an n minus 2 here, but I've got an n plus 1 here. In order to combine these sums, I need to make the powers match. So what I typically do is just make them meet in the middle. I mean, I just changed both of them to k, as it, n minus 2 is k and n plus 1 is k. If I do that, I get n is k plus 2 over here, and I get n is k minus 1 over there. And this one starts at order 1, and this one also starts at order 1. I think the reason I peeled off the 0th order term here is so that both of these would both start at linear order. I did that on purpose so that when we change the sum, these are already matching. If you didn't do that, then you have to look for exceptional cases, to peel them off. But there it is. So that gives me this equal to that, which of course immediately tells me a2 is 0, and k plus 2 times k plus 1 times a sub k plus 2 has to be equal to a sub k minus 1. And then I can solve that for the recurrence relation. A sub k plus 2 is equal to minus a sub k minus 1 over k plus 2 times k plus 1. One way I could ask a complete power series problem is I could, I could probably, bifurcate your solution process into find me the recurrence relation that describes the, an arbitrary high order piece according to the coefficient, right? So if I use those words, if I say find the general recurrence relation, I'm asking for you to find the equation like this on the coefficients, all right? So I might want to use that language on the test, and admittedly that language has not appeared in your homework or, in class too much, but if I do use that language, understand that this is the general recurrence relation, right? Now, if there are words on the test like that you don't understand, just come and ask me. I'll explain them, as long as it's not you being like, how do you solve this problem, Or which case is this? Is this like the one with the log, or is this the one without the log, or is this got the, like that kind of question, I'm going to be like, no. But if it's like, what do you mean by recurrence? Then I would try to say something vague about this being the general recurrence relation. Of course, that I would probably, if I was wiser, say find the general recurrence relation and explicitly list any special cases separately. In this case, the special case, a sub 2 is 0, and if I was, so anyway, it turns out that there's a triplicity, if you will. The coefficients are related by multiples of 3. So if you think about integers, the integers partition into multiples of 3 plus 1, and multiples of 3 plus 2, right? Those are disjoint partitions of the integers. And so if you want to understand all cases, you can consider those 3 just disjoint cases separately. Namely, the coefficient has the form 3j, or the coefficient has the form 3j plus 1. The coefficient of the form 3j plus 2, well, those are automatically 0, because the first one is 0. And when we add 3 to it, the recurrence relation forces the next, like a sub 5 to be 0, a sub 8 to be 0, a sub 11 to be 0, a sub 14 to be 0, a sub 17, and so forth, 17 to be 0. But on the other hand, these guys are related according to these, we substitute in the first relation to the second, to the third, and so forth. And, perhaps we can see some pattern. So when I say find the complete power series solution, I might say simplify if possible, and it may or may not be possible. Like I would say this, this is a fine solution. Don't forget I sometimes forget the way I've set this up. I've got division by j, right? So this is missing the j equals to 0 case, obviously, right? Because j equals 0 is not a happy place for this formula. So when I wrote this down, I was like, oh, yeah. And then I had to add 1 in order to pick up the 0th case, okay? And then over here, I was a little bit more knew where I was going, so I was like, oh, right, I don't have room to write this, but I squeezed it in. It's not great, but x plus this. You can do better than I did. On the test under time pressure, of course. But let's see here. I'm joking. Just do your best. Let's see here. Some of you said that the solution's 0 here, and you might be right. I haven't had time to thoroughly investigate this problem enough at the moment. Like, some of you said it was third order, and it looked to me like you had somewhat convincing arguments, like the higher order coefficients, which I have neglected to investigate. They end up implying that the lower order coefficients have to be 0. That might be true. It may be that I have to go to like a higher order to get non-trivial terms. Like, maybe the solution is 0 up to third order. I don't know. So I had taken points off, but I then recanted after about the 10th one I saw with 0. And I'm hoping that wasn't just one person spreading the 0. But anyway, it did seem reasonable, the arguments which led up to the 0, at least on one paper. And so I'm just not sure there, is what I'm trying to tell you. Let's see here. This one's also good in terms of a complete power series solution. A little bit different. This one's actually got the middle term, the y prime. And so I calculate y prime, y prime prime. And then I adjust by multiplying by 2x or x squared. And then I want to take 1, 2, and 3 and add them together. And when I do that, see, these are already, the nice thing about this particular problem is that they've already got like matching powers. See that? They end up having matching powers here with just a little bit of, maybe they just naturally come out like that. I can't remember. I guess they just naturally come out like that. This is, okay, well these two naturally come out to an n plus 1 power, but I had to make a substitution to convert this to n plus 1, which is why I did j plus 1. Anyway, so to add these three, I think of the n and the j all as n. So basically I make yet another substitution and replace j with n to combine these three. And that's why down here I've got, the 2 is that 2. The n is that n. There's a cn on both of them, so there's a cn. And then this is the n plus 3, n plus 2, cn plus 3 there. And this one's a little bit more interesting because there are two exceptional terms in the breakdown. There's this piece and that piece, which end up giving me C2 is 0 and C3 is minus 1/3 C naught. And then, of course, you got the general recurrence relation to deal with, which, much like the other problem we looked at today, has got this sort of three-plicity. It's relating, terms separated by 3. And it works out like this. That's what I got anyway. Hopefully, I was like, anytime I start at 0, I'm a little bit skeptical, but this is okay. Remember, 0 factorial is 1. That's okay. 3 to the 0, 1. So at least this formula is not wrong. A k equal to 0. And this one's, when you put a 0 in, I get a 1 here, so that's okay. Anyway, so yeah. So any questions?
Could you look at 48?
48. Yes, the Frobenius method is really not different than the complete power series method. The only wrinkle here, of course, is we have the initial equation to look out for, So when you go through the complete power series calculation, so it's the same thing as we were just doing, but the difference is now we have x to the n plus r, where r is a real, index or exponent, whatever you want to call it. And so the rules for differentiating such series is what you already know. I mean, term-by-term calculus still works for such things on the appropriate domain. And as such, we can go through the same kind of calculus we just did, differentiate once and twice, and then plug them in, and multiply by the 2x and the x here. And when we do that, we get this term plus that term. And then let's see here, I've got n plus r minus 1, n plus r minus 1, n plus r plus 1 over here. So to make this match up with these two, I make a n plus r plus 1 equals to j plus r minus 1 substitution to make the form of the exponent match up. After that substitution, then I have powers of the same type, which I can then combine. which then at this point reveals the general recurrence relation as the necessity of this vanishing. And then there are these exceptional terms over here. And what should always happen with the Frobenius problem is that when you do it, the lowest order term that you get will be it will just involve the whatchamacallit here, the index. So this is the indicial equation, maybe that one. I'm trying to remember. Let's see, this says either r is equal to, it starts at 2. So the only place these terms occur is here, right? So, oh, let me read on here. So from the lowest order term, we either have r equals to 0 or r equals to 1/2, all right? And 0 and 1/2 don't make this 0, I don't think, right? If I put a 0 here, I get 1, I get 1, if I put a 1/2, I get 3/2, I get 2. So I don't necessarily, I don't get this as 0 automatically. Is there does a sub 1 appear up in here again? I guess when I get to 3, I've got a sub 3 here, and I've got what? Uh, 3 minus 2, a sub 1. So I got to be careful. The 1 term is here, and it's also in here. So I think at the lowest order, the recurrence relation's a little fussy. A1 equal to, see, I don't believe that's true. Thus a sub 1 equal to 0. Oh, I'm bad. My bad. So here's why I'm wrong. The question isn't whether or not a sub 1 is in multiple terms. The question is whether or not this term stands alone from any others. And it does, you see, because what this whole calculation rests on is the linear independence of the n plus r power functions. So like this exponent and that exponent are distinct, all right? And there's a theorem of linear algebra that x to the power, like x to the p1 and x to the p2, these are linearly independent power functions. So if you have a summation of these things with coefficients on the powers equal to 0, it necessarily follows that the coefficients are all 0. All right, so like I have infinitely many equations from this single equation, one for each power, a distinct power. And so like from the x to the r minus 1 power, I have the indicial equation, which gives me that r is 0 and r is 1/2. But from this one, I get that forces a sub 1 equals to 0, since this one already forced r equal to 0. I mean, I guess logically speaking, you might wonder why isn't it the case that a0 is 0, and then that would force r equals to, you know, minus 1 or minus 1/2. And that might actually just be a different way of rewriting the same solution in this particular case. You think about it. But anyway, this is a solution, and I think it gets everything we need, because from the solution that I'm looking at here, we do get 2 linearly independent like general solutions from all this when we solve the recurrence. So this is my general recurrence relation, and so like I'm kind of torn on these ones. Is it best to solve the indicial equation first, find the exponents r, plug it in, and then find the recurrence relation? Or is it better to work out it symbolically with the r? I think it's probably better to work it out symbolically with the r in this kind of problem, and then find the r and plug it in to the recurrence relation, and then work through it. I don't know, I kind of go back and forth on what's the absolute best way to calculate these, but
Did you say we will not be tested on Frobenius?
I don't think I said that. Oh. Yeah. We should just not test on it?
Yeah, I think that's fine.
All right. I will allow it. So I will not have the full Frobenius solution on the test. All right, yeah. So, I will, however, almost certainly have partial Frobenius solutions on the test because the Cauchy-Euler problem is that. Because the Cauchy-Euler problem is a regular singular point, and the Frobenius method truncates to just the first two terms. That is what the Cauchy-Euler problem is. It is the Frobenius solution's most trivial and joyous case. But no, I will. This was for homework. I won't do this to you on the test. Don't worry. I'll save it for the final. I'm joking, probably. I'm joking. Joking. Where's the laughter? There's no laughter. Let's see here. So, notice for the Laplace transform, there are some things that you might need to brush up on if you don't know. One of those is like if I've got a product of sinusoids or, trigonometric functions, I can't take the Laplace transform of that. I need to convert it to a sum of sines before I can take the Laplace transform. So this might happen if you don't know about this trig identity, this business of imaginary exponentials, then you need to find something to take its place, all right? But you do have a page of notes, so I would encourage you to avail yourself of such knowledge. Or better yet, learn the imaginary exponential method because it's awesome. And then, here, Laplace transform of this, we have e to the minus 3s. Notice that we have to take the t and replace it by t plus 3. And we have to take the t here and replace it by t plus 6. And then I have to do, again, trigonometry, sine of t, cosine 6 plus sine of 6 cosine t. Then I can Laplace transform that to get this. And I of course also need to know that e to the 3 times e to the t is, that. So, let's see here. Another important thing that you must know is how to convert from a case-wise defined function to a sum of functions times unit step functions, right? If you forget what u of t means on the test, I'm going to tell you, but I'm not going to be happy. Like not knowing what the u of t means when you get to the test Friday, it indicates a severe lack of studying, or maybe you're in a car accident or something, or maybe I don't know, like something. Hopefully you had some sort of trauma, if you ask me that question. This is of course 0 if t is less than 2, and it's 1 if t is greater than 2, right? That's the unit step function. We built the gate functions, and so anyway, once we have that, then we can Laplace transform and so forth. All right, so I guess I'll stop there. Do not scatter just yet. I still have a few things to hand back to you guys who came in late. So just got everybody